Okay, so I think we should get started. I'm not sure where the rest of the class is. I guess they're all downstairs wondering what's going on, but hopefully they'll come up soon enough. So today we're going to move a little bit away from the complex analysis prerequisites that Stas was talking about, and we're going to go through some of the probability prerequisites. In particular, today's lecture is going to be focused on Brownian motion. Now, based on the questionnaire that you filled in, it seemed that most people had seen at least the definition. Some people had seen quite a lot. So I'm going to try and go through it relatively quickly. But if anything's unclear, then please just ask. In particular, the notation that I'm using might be different to the notation that you're used to. So just pop your hand up if anything's unclear, and I'll go over it in more detail. Okay, so what is Brownian motion? Well, the name Brownian motion comes from the botanist Brown, who in 1827 was looking at pollen through a microscope, and he noticed that these pollen particles in a water solution were making very, very erratic movements. And later on, it was discovered that these movements were caused by sort of being bombarded by water molecules hitting the pollen. And this sort of started to develop into a bit of a theory, and it took about 100 years for the mathematical theory to start to be formulated. And some of the key names in the mathematical theory, there was Einstein in 1905 who talked about Brownian motion, and then probably the biggest contributor was Loewner in 1923. And so the mathematical version of Brownian motion is often called a Loewner process after him. So what we're going to do today, we're going to just define Brownian motion and explore some of its properties. So I'll just start off with just reviewing some of the notation for stochastic processes. So this is a review of stochastic processes. Okay, so in particular, what's the definition of a stochastic process? Okay, so first of all, we need an index set. So let T be some index set. And the idea to have in mind is either a discrete index set, such as the non-negative integers, or a continuous index set, such as the non-negative reals. So what we want to be thinking of is 0, 1, 2 is discrete time. Or 0 up to infinity for continuous time. Okay, so we need an index set for a stochastic process. Then we need some measurable space. So let E with the curly E being the associated sigma algebra be some measurable space. And again, what are the sort of things to have in mind? Well, again, we can have a discrete measurable space or a continuous measurable space. So for a discrete space, you might want to be thinking about the integers together with the sort of power set on the integers as its associated sigma algebra of measurable sets. Or, so this is going to be discrete space. Or we can even take this in higher dimensions. Maybe we want z to the d and the associated power set sigma algebra on that. So that's a sort of discrete space to have in mind. Or we could take the reals together with the Borel sigma algebra, and that can be continuous space. Okay, so we've got an index set, we've got a measurable space. Well, what is a stochastic process? So given a probability space omega fp, a stochastic process is a measurable map X, which goes from the sample space together with the with its sigma algebra to what I'm going to call the space of functions, of measurable functions from our index set to E. So this is a notation that I'm using to mean the set of all possible functions from T to E, all possible measurable functions. Okay, well, what does that mean? That means that so X maps every omega in omega to a measurable function x of omega, which is equal to all the values that this function can take at t for all t in our index set. And this is in our space of functions from the index set t to e. Okay, and then just a couple of comments. So for each fixed t in our index set, we require that the set xt of omega, where omega is in omega, is a random variable. Okay, so what have I done here? So if I fix t, then essentially for every omega, instead of having a whole function, for fixed t, I just get for every omega, I assign some value in the set E, so some real value or some integer value. And what I need to know is that this gives me a random function from omega to the set E, and I need that random function to be a random variable. So, i.e., we need that the set xt less than or equal to x must be in our sigma algebra associated with our probability space for each x in the reals. And then lastly, one final definition connected with stochastic processes is for each fixed omega, we can consider the set xt omega as t runs through the index set, and this is called the sample path of the process. Okay, so essentially what's happening is with what a stochastic process is it's something that depends on both the element in the probability space and the index set. So for each omega and for each time, there's associated a value in E, which you can think of as a real value or an integer value. And it's done in such a way that as you run through all of the t's, so you fix omega and run through all of the t's, you get a function called the sample path, or you can fix t and consider this as a function of omega, and that gives you a random variable. So you can sort of fix t, think of it as a function of omega, or fix omega, think of it as a function as t, and it satisfies these properties. Okay, any questions on that definition? Okay, so just a few more associated definitions. So the next one is finite-dimensional distributions. Okay, so these, we can call them the finite-dimensional distributions of a stochastic process X. Are the distributions of the finite-dimensional vectors xt1, xt2 up to xtn, where t1 strictly less than tn all lie in t, and we need to know these distributions for all possible times t1 up to tn. So this is for all and all n in n. And you can show that the finite-dimensional distributions determine the distribution of the stochastic process. So if we want to be modulo some mild assumptions on the type of stochastic process. So if you want to be describing a particular stochastic process, it's enough to be able to give the description of the finite-dimensional distributions for all choices of times and all natural numbers and natural numbers n. Okay, so let's just see a simple example of a stochastic process. So this is one I think that you've all seen before. So this is the simple random walk. So here we've got xt, and time runs through the natural numbers. So this is a discrete time process, is determined by probability that xn xt equals xt minus 1 plus 1 is equal to p. Probability that xt is equal to xt minus 1 is equal to q, which is 1 minus p, and each step is independent. Of all other steps. Okay, so here's our sort of picture. Got time on this axis, and it's a integer time valued process, so times 1, 2, 3, 4, 5. And what we do is we say start off at 0, and then you toss your coin, and with probability p we go up to 1. Probability q we come back down again. So just keep tossing our coin, and your simple random walk looks something like that. Okay, so I think everyone's seen that before. So I just wanted to give these definitions just so that we agreed on notation. So any questions on any of this? Okay. Okay, so Brownian motion is an example of something called a Gaussian process. So let's look at Gaussian processes. And again, just to recall the definition of the multivariate Gaussian distribution. Okay, so this is a distribution for a random vector x equals x1 up to xn. And this has a n-dimensional multivariate normal distribution. If its probability density function is given by fxx is equal to 1 over 2 pi to the n over 2 square root of the determinant of sigma exponential of minus 1/2 x minus mu sigma inverse x minus mu transpose. This is for x in r to the n, where mu is also in r to n, is the vector of means. And so mu I is equal to expected value of xi, and sigma is the n by n covariance matrix. So, in other words, sigma ij, the ijth component of this matrix, is equal to the covariance of xi and xj. Okay, and the way we write this is we'll write x some multivariate normal mu and sigma. Okay, so there's a few properties of this distribution which hopefully you're familiar with. So the first property is that if you just want to know what the distribution is of a single variable, so just say x1 or x3 or something like that, rather than the joint distribution, then it's a normal random variable with mean mu I and variance sigma I. So properties. So one is that for all I, xi is just a normal random variable with mean mu I and variance sigma I. The second property is that x1 up to xn are independent if and only if sigma is diagonal. So this is a very special property of the multivariate normal. So normally, you know, if two random variables are independent, you know they have covariance 0, but the converse doesn't usually apply. So in general, if you have two random variables with 0 covariance, that doesn't mean that they're independent. However, for the multivariate Gaussian, that does mean they're independent. So this is one of the few distributions which has this property that independence is exactly equivalent to the covariance being 0. Yep.
Just a quick, how is the one compatible with the two in the sense that if the sigma is not diagonal, how can I give a distribution for each xi independently of the other ones?
So what you want to do, so to find the marginal distribution of this, so what I need to do is I need to ask myself what is the distribution of x regardless of what all the other random variables are. And so yeah, so you fix one component, you integrate out everything else. You renormalize, and if you do that, you'll find this property. In fact, it's maybe quite a good exercise to sort of see. It's essentially matrix multiplication, but if you do it, you can deduce this from this property. Okay. Any other questions? Okay, and then the third property is that if A is any real valued m by n matrix, then A times the transpose of x is also a multivariate normal with mean given by A times the transpose of mu and covariance matrix given by A sigma transpose of A. Okay, so this is another very, very useful property, is that multivariate normals are preserved under, the distribution is preserved under linear transformation. So if I take any multivariate random vector, take any linear transformation of that, I still have a multivariate normal, but with new parameters. Okay, and so this leads us to what I want to talk about, which is Gaussian processes. So here's the definition of a Gaussian process. So a Gaussian process is any stochastic process whose finite dimensional distributions are multivariate Gaussians. Okay, so I give you a stochastic process. It's determined by its finite dimensional distribution, so you need to pick for every single n and for every single set of times t1 up to tn, you need to work out what the finite dimensional distribution function is, and f for every single one of those we get some multivariate Gaussian, then we have what we call a Gaussian process. Okay. Okay, so just a couple of examples. Okay, so when I give the examples, as I said, because the Gaussian distribution is only determined by its mean and covariance matrix, if I want to give you the finite dimensional distributions, I just need to give you the finite dimensional, I just need to give you the vector of means and the pairwise covariances, and tell you it's Gaussian, and then you can work out all the distributions. So in the examples I'm going to give you, I'm just going to give you enough information that you can then work out the expectation vector, you can work out the covariance vector, covariance matrix, and because you know it's a Gaussian process, you then know all the finite dimensional distributions. Okay, so here's the simplest example of a Gaussian process. So this is discrete Gaussian white noise. So this one, the index set is discrete, so t is equal to 0, 1, etc. And each xi is independent, identically distributed, normal 0 sigma squared random variable. So again, this gives me enough information to work out the finite dimensional distributions, because what do I need? Well, I need the vector of means, and I need the variance covariance matrix corresponding to that. Well, that means I need mu j for each j, but I'm told each of these is 0 mean, so that one's fine. So this is equal to 0 for all j, and I need the covariance vectors, but I'm told that they're independent, so this is 0 unless I is equal to j, in which case we get sigma squared. And so then if I give you any sort of n and say what's the finite dimensional distribution with that n, we just have this just becomes a vector of length n containing zeros, and this is a diagonal vector, so diagonal n by n matrix with sigma squareds all the way down the diagonal. Okay, and well, what does it look like? If you're going to draw a picture, again, it's discrete in time. And at each point, I just need to generate a normal 0 sigma squared random variable. So just completely independent. So you end up getting something that looks a little bit of a mess. But that's what we have. Okay, and then just one second example. So this one is the Gaussian random walk. So again, we take our index set t to be the non-negative integers. And this time, each step, xn minus 1 is an IID normal 0 sigma squared random variable. Okay, so it's a bit like the simple random walk. We had each step was an IID Bernoulli random variable. It was either taking the value 1 or minus 1. This time it can take any real value. So this is a discrete space process. So this is discrete time but continuous space. And again, this time writing down the finite dimensional distribution is a little bit harder. It's not too difficult to show that the mean vector is still all zeros, but working out the variance covariance matrix takes a little bit of work, because we only know that the steps are independent now, not the individual components. Okay, so before we can define Brownian motion, we just need just a couple more definitions. So a stochastic process is stationary if the finite dimensional distributions are invariant and the shifts in time. I.e., what do I mean by that? If xt1 plus h to xtn plus h has the same distribution as xt1 up to xtn for all choices of n greater than or equal to 1, t1 to tn in t, and h such that t1 plus h up to tn plus h are all in t as well. Okay, so essentially all that means is if I just pick particular points in time and look at the finite dimensional distributions, and then I just shifted everything by a certain amount and looked at the finite dimensional distributions by that complete shift, the distribution wouldn't be any different. And you just need to be a little bit careful here with the index sets that we're mostly using. So with the with the integers or with the positive reals, as long as you're shifting by an h that sort of keeps say it's integers. If h is an integer, then you're right. But you could imagine having an index set where my index set is the primes, for example, and then you're not going to be finding an h for which has this property. So that's the only thing you just need to be careful about. Your shift still keeps you in the index set. Okay, slightly related but also a bit different is a stochastic process has stationary increments. If xt2 minus xt1 to xtn minus xtn minus 1 has the same distribution as xt2 plus h minus xt1 plus h, xtn plus h minus n minus 1 plus h for all n t1 to tn and h as above. And the final definition that we need is a stochastic process has independent increments if xt2 minus xt1 to xtn minus xtn minus 1 are independent random variables for all n greater or equal to 1 and t1 up to tn in t. Okay, so let's think about the stochastic processes that we've looked at so far. So which ones were stationary? Can just people shout out which were the stationary stochastic processes that we've looked at?
White noise.
Gaussian white noise, yep, that's a stationary one. Any others?
Random walk.
Okay, this was a slight trick question. A random walk is not a stationary random variable. For instance, if you just think about our simple random walk that could only take the value, so I'll just reuse this picture. At time 1, our random walk can only be the values 1 or minus 1, right? Whereas at some time in the future, at say time 5, it could go all the way between minus 5 and plus 5, right? So it's not going to be stationary. If you shift in time, you don't keep the same distributions. Okay, so that I'm glad someone mentioned that. Simple random walk is not an example of a stationary process. However, what about stationary increments? It does have stationary increments. Absolutely right, because between any two, the increments are just given by a Bernoulli random variable, and so if you take any sort of distance, it's the sum of Bernoulli random variables, and that's the same for any shift, and so the distributions are stationary. And what about independent increments? Which ones have independent increments? Right. So they all do. Because again, with the I mean, the white noise does because everything's independent. With the other ones, with the random walks, the one-step increments are independent, and so if you take sort of gaps between these are non-overlapping, times, and so again they're independent because they're sums of independent random variables. Okay, so the main thing I just wanted people to sort of be clear in their mind is that random walks are not stationary processes, but they have stationary increments. So that's something you just need to be a little bit aware of. Okay, so that's everything we need now, and now we can start defining Brownian motion. Okay, so definition and construction. Okay, so here's our definition. And I'm going to call it definition 1 because we'll see 2 definitions of Brownian motion, but this is the first one. Okay, so a continuous time stochastic process Bt, t greater than or equal to 0, is a Brownian motion if the following properties hold. So B0 is equal to 0, so we start it at 0. You can put almost surely there. For every 0 less than or equal to s less than t, Bt minus Bs is normal 0 t minus s. C is that Bt has stationary and independent increments. And last one is that Bt is continuous in T, almost surely. So I think might as well have a less than or equal to that. Okay, and then just I think I mentioned this in the introduction, is that Brownian motion is also sometimes called the Wiener process. And people sometimes use the letter W for Brownian motions instead of B for that reason. Okay, so just a few remarks about this definition. So one is that A can be replaced by B naught is equal to X to give what we call Brownian motion started at an X. Remark number 2 is that B can be replaced by Bt minus Bs is normal 0 sigma squared T minus S, and this we say to give Brownian motion with diffusivity sigma squared. And in that case, this one where we've got sigma equals 1, which we have here, is we sort of refer to as a standard Brownian motion. Then remark number 3 is that conditions B and C together determine the finite dimensional distributions. Of B. And in particular, if we look at B and C, we know that an individual increment is a Gaussian process, and we know we've got the stationary and independent increment property. And so if you use those two things together and you try and write down the finite dimensional distributions using it, what you'll find is that you get a Gaussian process out of this. So you'll find you get a multivariate normal distribution for any one of the finite dimensional distributions. And so that means that Brownian motion is a Gaussian process. So, and in particular, B is a Gaussian process. And then finally, we can generalize this definition to higher dimensions. So a d-dimensional Brownian motion is a vector bt1, bt2 to btd, t greater than or equal to 0, where the bti are IID Brownian motions. Okay, so what do I want if I want a high dimensional Brownian motion? Well, each component is itself a Brownian motion, and each component is independent of the others. And so this is independent in pairs. This is important. And then complex Brownian motion is the process bt equals bt1 plus I times bt2, where bt1, bt2 is a 2-dimensional Brownian motion. Okay, so we can talk about Brownian motion in the complex plane as well, and it's just exactly the same as the 2-dimensional Brownian motion under the identification between the plane and the complex plane. Okay, but unless we specify otherwise, we won't go with these sort of generalizations. We'll just take standard Brownian motion satisfying these definitions over here. Okay, so as I sort of argued, that if you use B and C carefully, you can show that Brownian motion is a Gaussian process. And in fact, this is an exercise on the exercise sheet. And we know that Gaussian processes are completely determined by just knowing the expectation vector for each xt and the pairwise covariances for each. And so because of that, we can actually use the theory of Gaussian processes to write down an alternative definition for Brownian motion, which turns out to be a little bit easier to work with in practice. So let's write down the alternative definition. And as I said, showing their equivalent is on the exercise sheet. Okay, so here's our second definition. So a continuous time Gaussian process Bt is a Brownian motion again we need some properties, so the first one is the same, that B0 is equal to 0 almost surely. Second one is that the expected value of Bt is equal to 0 for all t. The third one is that the covariance of Bs and Bt is equal to the minimum of S and T. Does everyone know this notation? No, okay. So this is exactly means the minimum of S and T. And if you want the maximum, you do a sort of V-shaped. Okay, so the covariance of this, and this is for all S and T. And lastly, Bt is continuous, almost surely in, so it's continuous in t greater than or equal to 0, almost surely. Okay, so if you compare these two definitions, so what are the key differences? Well, this one we just had a continuous time stochastic process. This one we've specified as a Gaussian process. Okay, and so immediately we've got a lot more information at the start of this one that it's a Gaussian process, and so because of that we only need to specify the expectation and covariance in order to fully specify the definition. For this one here, we needed to specify that the increments were normal because there was nothing before that said that we had any Gaussian properties at all, and we needed stationary independent increments. Okay, and so this is the exercise that you need to do, is essentially show that these two conditions, knowing that the increments are normal and that it's got stationary independent increments, is the same as knowing it's a Gaussian process with this expectation and this covariance. Okay, and as I said, so that's an exercise for you to do for next week. Okay, can anyone think of any reason why it's not okay to just take these definitions and now start studying them? Existence, right? I mean, we're imposing a lot of structure on this process. You know, we're imposing sort of a behavior for every single pair S and T, and you know this is for all real numbers. And so, you know, we've got uncountably many constraints on our process here that we're imposing, and there's no reason a priori why they need to all be simultaneously satisfied. You know, it might turn out that somehow having a covariance like this just means it's impossible that it's continuous. So it's quite an important problem to actually prove that Brownian motion does actually exist as a process. Now I'm not actually going to show this in this course, but if you look at any good textbook on Brownian motion, you'll see that. But what I will show in the next slot, we'll have a little break now. But what I will show is that Brownian motion does arise very, very naturally as a limit of random walks. And while that doesn't quite prove existence, it sort of motivates that actually these are quite natural assumptions. Okay, so we'll break now until 1:15, and then in the next session I'll sort of show the relationship with simple random walks, and we'll look at some properties out of Brownian motion. Okay, in the meantime, if you've got any questions, I'll be standing here. So. Just thinking back to the very start of the lecture where I sort of mentioned that Brownian motion was first observed as so pollen being bombarded by water molecules, you can sort of see this is actually quite a good description for what's happening, because each of these random variables in some sense can be the hit, the push given by a particular water molecule, and each water molecule is giving a different push independently of all the others, and so the total push that our pollen particle experiences after n steps is given by the sum of random variables. And so if you rescale, so you make all of the pushes very, very small, sort of rescale the effect of each push by root n, but you look over long time periods, so there's time for the particle to receive lots and lots of little pushes, then you expect its displacement to be approximately Gaussian. And so that's why it's sort of this mathematical object that I wrote down is actually a very good model for the sort of physical process of pollen particles being hit by little particles. Okay, so here's our theorem, our sort of analogous theorem to this, but for stochastic processes. Okay, so let y1, y2 be a sequence of IID random variables with mean 0 and variance 1. And for each n greater than or equal to 1, define the stochastic process Ztn. So now we've got an index t, because we want to define a process, to be the sum from I equals 1 up to the floor of n times t of yi divided by root n, and that's for t greater than or equal to 0. And do you all know this notation? This is the largest integer that's less than or equal to nt. So if you took t equals 1, then the largest integer less than or equal to n times 1 is n, that one's fine. If you took t equals 1/2, then n over 2 may not be an integer, so you go to the biggest integer less than that. Okay, so what we've done here is we've sort of generalized this definition. This can be sort of viewed as taking t equals 1 in this expression here, but we've managed to define it for all values of t. Okay, and if t is if this is strictly less than 1, so we're summing from 1 to 0, if you're worried about that, we just interpret that as meaning the zero sum. Okay, so what's our theorem statement? Then for any k greater than or equal to 1 and 0 less than or equal to t1 less than or equal to tk and z1 up to zk in the reals, the limit as n goes to infinity, the probability that tin is less than or equal to zi for 1 less than or equal to I less than or equal to k is equal to the probability that bti is less than or equal to zi 1 less than or equal to I less than or equal to k. Okay, so what have I written down here? Well, this is just a finite dimensional distribution function corresponding to Brownian motion. This is the finite dimensional distribution function corresponding to our process Ztn. And so what we're saying is that in the limit as n goes to infinity, this finite dimensional distribution function converges to this finite dimensional distribution function. And that's exactly what we had here, except here we only had a one-dimensional vector. And so, but we were still saying this distribution function of Zn converges to this distribution function of a normal 0, 1. Okay, and the notation that I sometimes use here for convergence in distribution is the sort of double-headed arrow. So central limit theorem can be thought of as saying Zn converges in distribution to Z. In this case here, we can write Ztn t greater than or equal to 0 converges in distribution to bt t greater than or equal to 0. So what we mean here is the finite dimensional distributions of this process converge to the finite dimensional distributions of this process. Okay, so how do we prove this? Well, in essence, we sort of need to, in some way, write down a computation for this, and then write this in a way that we can apply the central limit theorem and deduce this. I'm only going to do it in the case when k is equal to 2. So I'll just show that the joint distribution of two random variables, the random variable corresponding to 2 different times here, converges to Brownian motion at 2 different times. That's mainly just to keep the notation simple. The mathematical ideas are the same, so you should be able to take my argument for k equals 2 and write it down for general k. But just to save on sort of board space, I'm just going to do it in the k equals 2 case. Okay, so here's our proof. And we just do this for k equals 2. Okay, so suppose 0 between s is between less than or equal to t. Now we know that the Gaussian distribution has this linearity property, that if I take any linear transformation of a Gaussian process, I still have a Gaussian process just with the mean and covariance matrix transformed according to the formula that I wrote down before. And so I can apply a linear transformation to the zi's in this expression, and as long as I apply the same linear transformation to the bti's in this expression, if I can show my linearly transformed processes converge, then I can just do the inverse linear transformations and I'll get my result. So it's enough to establish this for a specific linear transformation. So let's write that down. So by linearity properties, so in order to show that ZSN, ZTN converges in distribution to BS, BT, it is sufficient to show that ZS, ZT minus ZS converges in distribution to BS, BT minus BS. Okay, because if I know the finite dimension, if I know the distribution of this, using properties of the multivariate normal distribution, I can work out the distribution of that. Likewise, if I know the distribution of this, again, just by applying my linear transformation to the multivariate normal, I can get the distribution of this. And so if these two behave the same way, it's the same transformation gives me these two behaving the same way. Okay, but this is kind of a nice process because well, we can just write down what ZTN minus ZSN is equal to. Well, it's just the sum from the floor of ns plus 1 to the floor of nt of the yi's, because I've just subtracted off the sum up to ns. And since the yi's are independent, that means that this is completely independent of the sum up to ns. So zt minus zs is independent of zs. And okay, so since that and the yi are independent, ZTN minus ZSN and ZSN are independent. Therefore, what's the joint distribution of these two? So probably that ZSN less than or equal to Z and ZTN minus Zn less than or equal to W is just the product of these two. Okay, so let's have a look at this distribution over here. So we need to analyze how this process behaves. Okay, well, we can do a little trick here. So we can write Ztn minus Zsn as the sum from I equals floor of ns plus 1 up to nt of the yi's divided by square root of the floor of nt minus floor of ns times by square root of floor of nt minus floor of ns divided by square root of n. Okay, so all I've done here is I've just divided by and multiplied by the same term. But why was this a good thing to do? Well, how many terms do I have in this expression? I've got exactly this number of terms. And so this expression here is exactly in the form of this expression here from my central limit theorem, just with n replaced by floor of nt minus floor of ns. And so by the central limit theorem, this one here converges to a normal 0, 1. So this is by the central limit theorem. What about this one here? Well, this is just a simple analysis. If you just use simple analysis there and let n go to infinity, you can show that this converges to square root of t minus s. So this is just analysis. Okay, and so that means that we know that zt minus ns converges in distribution to square root of t minus s times a normal random variable. And so hence this probability of Ztn minus Zs less than or equal to w, limit as n goes to infinity of that, is equal to the probability distribution of a root t minus s times a normal being less than w. And so that's just the normal distribution function at w divided by t minus s. But this is exactly equal to the distribution function of bt minus bs being less than or equal to w. Because by properties of Brownian motion, we know that bt minus bs is a normal random variable with mean t minus s, and so that means we can write it as square root of t minus s times a normal 0, 1 random variable. And so this just follows directly from properties of Brownian motion. Okay, so using that z naught n is equal to b naught is equal to 0, so using that both processes start from 0, we could just set s equals 0 in both of these things and t equals s, and so that gives us we get that probability that Zsn less than or equal to z converges to probability that bs is less than or equal to z. So that's exactly the same argument, just because we know that these two are equal to 0. And so putting it together, we get what we want. Limit as n goes to infinity, probability of Zs being less than or equal to z and Ztn minus Zsn being less than or equal to w is equal to probability that bs is less than or equal to z, bt minus bs being less than or equal to w. But there's one final step here. We know that Brownian motion has independent increments. That was another property of Brownian motion. And so this product is exactly equal to probability that bs is less than or equal to z and bt minus bs being less than or equal to w. And that proves our result. Okay, so I've done this in the case when k is equal to 2, But in general, if you've got any sequence of k random variables here, you just need to do a similar transformation to this, use independence, use the central limit theorem for each of these components, put it all back together again, and it works in exactly the same way. So there's really no difference between the k equals 2 argument and the general k argument. You just have a bit more work to work out the linear transformation between this with k vectors in and the independent increments, but it's essentially all the ideas are exactly the same. Okay, any questions on that? Okay, so I said I haven't proved existence with this proof because there's various other aspects that you need to check. So continuity, it turns out to be sort of one that can be a little bit awkward to check. Convergence as a stochastic process, I haven't done in the sort of space of stochastic processes. I've just shown convergence of finite dimensional distributions. So there's some missing elements there. But if you want to look at the proof of existence, as I said, any textbook on Brownian motion will give it in. But what you can hopefully see with this proof is why the conditions are sort of natural conditions to have for this process. Okay, so the next thing we're going to look at is transformations of Brownian motion. Okay, so what makes Brownian motion quite convenient to work with is that there's certain sort of transformations that you can do to it which preserve the distribution. So it's invariant under certain transformations. So here's our next theorem. So let Bt be a Brownian motion. Then each of the following is also a Brownian motion. Okay, so first one is reflection. So if we set Wt to be equal to minus Bt for t greater than or equal to 0. Okay, so I take my Brownian motion picture. So actually, I should say this existence proof kind of starts giving an idea of what Brownian motion should look like. Essentially, it's a simple random walk, but really sped up, and so sort of Brownian motion tends to look a little bit like this, and you can do a simulation pretty easily just by simulating a random walk and then just speeding it up, speed up time by n, shrink space by root n, and you get this. So what does this reflection result say? Well, if we take the reflection of Brownian motion, this green process is also a Brownian motion. Okay, and how do you do that? Well, you just need to check the properties. So you just need to go through, look at the definition of Brownian motion. The definition consists of 4 properties, and you just need to go through and check them one by one. Okay, second one. Okay, I call this the Markov property. There's a lot of different Markov properties. So this is, I just guess this is my name rather than an official name. But essentially it tells you that you can sort of restart Brownian motion at a later point in time, and it still looks like Brownian motion. So if we set Wt to be equal to Bt plus T minus Bt, T greater than or equal to 0 for any fixed T. Okay, so again, let's look at our picture. So what have we done now? So let's take some time, some fixed time t, and what I do is I look at Brownian motion from that point t onwards. So that's this process over here, but I subtract the value at t. So I take my axes down to there, and this result says, well, this process here, if you hide all of these things, if you sort of hide everything you've seen up to this point, and you just look at the process from that point recentered to start at 0, then that itself is a Brownian motion as well. And actually, you can go further and say this Brownian motion is independent of its past. Okay, third property is time reversal. So now we let Wt be equal to Bt minus Bt minus T, 0 less than or equal to T less than or equal to T for any fixed T. Okay, so this one is only defining a stochastic process on a bounded interval, but given that we've got a stochastic process restricted to this bounded interval, it still satisfies all of the conditions of Brownian motion. And so essentially, what have I done over here for that picture? I've taken my time t, and I'm running it backwards in time. So as time goes forwards, I'm tracing. Well, first of all, I reset it. I subtract. I take it down so it starts at 0, and then I sort of follow this process backwards in time. Well, it's the reflected process backwards in time. So I'm subtracting, and what I argue is if I then flip that forwards, that itself also looks like a Brownian motion. Okay, so essentially Brownian motion run backwards in time also looks like Brownian motion. Here's this next one is rescaling. So Wt is equal to c to the minus half b ct, where c is greater than 0. Okay, so what I do with this one, I take my Brownian motion and I change my time scale. So you can think of that as sort of stretching the time axis or shrinking the time axis, depending whether c is bigger or less than 1. But you're changing the time axis by a factor of c. And at the same time, you're shrinking the y-axis. So or expanding it again, depending on whether c is greater or less than 1. But you're sort of rescaling. You're rescaling the time axis by a stretch of c, and you're rescaling the space axis by a stretch of 1 over root c. If you look at the picture that you have under this rescaling, again we still have a Brownian motion. And this one is particularly important because this tells us that Brownian motion looks the same on different scales. You know, I can take some sort of small interval of size 1 over c, and then I can stretch it to size c, and it's going to look the same. And so this is the one that tells us that Brownian motion is a fractal process. It looks the same on different scales. If you zoom in or you zoom out, it doesn't change what it looks like. So this is a really important one. And one final one is inversion. So here we've got Wt is equal to T be 1 over T greater than 0. And you can see with this one, this doesn't make sense when T is actually equal to 0, so I need to define separately that W0 is equal to 0. Okay, and this one again is kind of interesting. This sort of tells me that I can sort of invert time. So if I want to know what happens when my Brownian motion has a very, very large time, well, that's the same as when this W has a very, very small time. And so I'm sort of flipping over time. I'm turning properties of Brownian motion at large time into properties at small time. And so this one is very, very useful if you want to study the way Brownian motion behaves over very long time periods. You can turn it into questions about how Brownian motion behaves over very small time periods. And there's an exercise on the example sheet where using this transformation will be pretty useful to you. Okay, so any questions about those transformations? So the proof of this theorem is an exercise. So this is again on next week's exercise sheet for next week. And the only hint I'll give you is choose which definition of Brownian motion to work with carefully. If you choose the wrong definition, you make life harder for yourself. So there's two definitions we've given. With one definition, these tend to be kind of easy. With the other definition, they're kind of a bit harder. So that's the only hint I'll give is choose the right definition. And in that case, I think it's quite a straightforward exercise to do. Okay, so Brownian motion's invariant under all these transformations, but you can actually do other transformations to Brownian motion, which it's not invariant under, but also actually gives it sort of interesting, useful processes. Okay, so other processes. Can be constructed from Brownian motion. So the first one is Brownian motion with drift. So xt is equal to mu t plus sigma bt for c greater than or equal to 0. So what do? Well, we multiply our Brownian motion by sigma, so we effectively change the diffusivity of this, change our random variables to have variance proportional to sigma squared, and then we add in a linear transformation. And so you tend to get a picture, if this is the line mu t, you sort of have a process which kind of follows that sort of trend, but with sort of fluctuations around it. Okay, second one is geometric Brownian motion. So xt is equal to e to the mu t plus sigma bt. So essentially we take our Brownian motion with drift and we just take the exponential of it. And one immediate property you can see with this is it's always non-negative. This is always taking non-negative values. And this is actually proposed in the finance world. This is used as a good model for stock prices, because stock prices should have these random fluctuations corresponding to little incremental kicks from every transaction that's taking place. But we need something that's not going to be negative. The stock prices, they can go to 0. Your stock can lose all its value, but it's not going to go negative. You'll never find you suddenly have to sort of pay for all of the assets that you hold. And so geometric Brownian motion is quite an important process in mathematical finance. And then the third one is the Brownian bridge. So xt is equal to bt minus t times b1, and this one's only defined for for t between 0 and 1. But if you look at this one, well, what happens at time 0? Well, at time 0, we've got 0 minus 0, so it starts at 0. And what about at time 1? well, we've got b1 minus 1 times b1, so it also stops at 0. And so the Brownian motion is sort of a Brownian process, but it's pinned at the values 0 and 1. And that's why it's called a Brownian bridge, because it's a sort of bridge between, you know, you can imagine your two banks of the river being at the same level, and you take sort of some stochastic walk excursion between the two, but you end up back at the same level. Okay, so just a quick question. We'll just do it with a show of hands. Is this a Gaussian process? So put your hands up if you think it's a Gaussian process. And if you think it's not a Gaussian process. Okay. 0 marks for participation. What about this one? Who thinks this one's a Gaussian process? Who thinks it's not a Gaussian process? Okay, and how about this one? Who thinks this one's a Gaussian process? And who says no? Okay, so modulo not participating, you're essentially right. This one is a Gaussian process, this one is a Gaussian process, and you can show that just by, we're just doing linear transformations of Gaussians. And so because of that, it's easy to show that the finite dimensional distributions are Gaussians. This one, you're not doing a linear transformation of a Gaussian. And in fact, the fact it can only take non-negative values immediately tells you it can't be a Gaussian process. So this one isn't, but these two are. Okay, any questions on those transformations? Okay, so we'll just finish the lecture by looking at something called the reflection principle. So let's just clear the board. Okay, so essentially what we know by this theorem over here is that if Bt is a Brownian motion, then also we have this Markov property telling us that if you look at the process from time t onwards, sort of just pulled back to start at 0, then that is itself a Brownian motion. And as I said, it's not too difficult to show that this is independent of the previous path. Also, we know by this property that the negative of Brownian motion is itself a Brownian motion. So if I look at the negative of this, that also gives me a Brownian motion. And that means that if I define a new process here, so let's define Wt to be equal to Bt if we're less than or equal to t, and Bt plus Bt minus Bt, which is just equal to 2Bt minus Bt. So this is for t less than or equal to t, and this is for t greater than t. So let's just draw a picture to show you what I'm defining here. Okay, so here's my this is my Bt process. Okay, so that's Bt, and here is my capital T. So what am I doing? What is Wt? Well, Wt agrees with Bt up until this time capital T. And then what happens? Well, then I take the value at time t, but I add in minus bt minus bt. So I'm reflecting what's going on over here. So it's quite hard to draw this. But in essence, this is what we have. So this in pink I've got here is Wt. Okay, so I've run a process up to a fixed time, and then instead of following my original trajectory, I just reflect that original trajectory from that point where we agreed. Okay, and so what do we know? Well, we know that this segment up to here is a Brownian motion because it's just a Brownian motion restricted to a finite time interval. We know this bit onwards is a Brownian motion because of the Markov property, and it's independent of this by independent increments. And therefore we know that this reflected one is also a Brownian motion because of the reflection property, and it's independent of what happened before, and so that means that the pink process is itself a Brownian motion. So by the transformations of Brownian motion, and independent increments, Wt is a Brownian motion. Okay, and if you don't like proof by picture, you can just work out the finite dimensional distributions for these and just consider the cases whether we're above or below t. And if you do that and use the independence carefully, you'll get the finite dimensional distributions of the Brownian motion. Okay, now it turns out that this statement held for a fixed value t, but actually the same result holds if we replace t by a stopping time. So has everyone seen stopping times before? A few of you haven't. Okay, so what I'm going to do in this lecture, I'll give a slightly informal definition of a stopping time, and then in next week I'll define stopping times formally. Okay, so for now, the definition is not 100% rigorous, but it should be enough to understand this result and how to apply it, and then next week we'll put in the machinery to define it properly. Okay, so let's go for our definition. So this is stopping time. Right, so a random time is a random variable taking values in 0 up to infinity. So it only takes non-negative values, but it can actually take the value infinity. So this is a closed interval here, so just bear that in mind. And then a stopping time is a random time t. So stopping time for the process Bt is a random time such that the event t less than or equal to t depends only on the history of B up to time t, i.e. on Bs 0 less than or equal to S less than or equal to t. Okay, so this one I'm being a little bit imprecise because I haven't really defined what I mean by history. In the next lecture I'll explain what I mean by that. But intuitively, something is a stopping time if you can just tell whether it's happened or not by time t by looking at the process up to time t. Okay, so here's an important example. This is what we call a hitting time. So let's define TA to be the first time such that our process hits the level A, where TA is equal to infinity if A is never reached. Okay, so what do I need to do to know whether my hitting times happened before this particular time point? Well, I just need to look at my level A, and then I just have to look at the path up until this point, and if the path has hit my level A, my stopping time has happened. If my path hasn't hit it by this point, then that event hasn't happened, and I don't care what happens beyond that event. I can decide on the truth of this event, I can decide whether this event occurred or not, only by looking at the process up to time t. And so that's why it's an example of a stopping time. What's not a stopping time is the last time that I might hit a process. So I might say, let t be the last time before time 1 that I hit the level A. So here's level 1. Well, now here's my point t. Do I know whether the stopping time has happened or not by time t? Well, I need to know whether it hits that level A after this time. And so I can't decide just by looking at that process. So the last time to hit is not a stopping time. The first time to hit is a stopping time. So those are sort of canonical examples to have in mind. And it turns out that we can replace t by any stopping time in this result, and we still get a Brownian motion. So let me just quickly write up. I know I'm almost out of time, but I'll just write a couple of quick results up just to explain that in words. Okay, so here's a theorem called the strong Markov property. Okay, so let t be a finite stopping time. And let Wt be equal to b t plus t minus bt for t greater than or equal to 0. Then Wt is a Brownian motion and is independent of bt 0 less than or equal to t less than or equal to t. Okay, so this is exactly the same as this result that I called the Markov property in the exercises. The big difference here is t can be random now, but it can't just be any random variable. It has to be a finite stopping time. But if it's a finite stopping time, then we still have this process. And then using the Markov property, we can generalize the reflection principle. So here's our theorem. So this is reflection principle. So let t be a stopping time. And define WT to be BT if t is less than or equal to t, or 2b capital T minus BT if t is strictly bigger than t, then WT is a Brownian motion. Okay, and I'll just quickly in the last, well, minus 3 minutes, just do an example of how powerful this result is. Okay, so here's an example. So let MT be the supremum over 0 less than or equal to s less than or equal to t, b of s. Okay, so this is the maximum value taken by Brownian motion up to the time t. And what I want to do is find the distribution of m of t. Okay, now this is quite a difficult thing that we're trying to do, right? Because we're trying to find an uncountable maximum, so a maximum taken over uncountably many random variables. And we're trying to find its distribution. So any way that you have for finding distributions, you can't write down the joint distribution of this because we've got uncountably many variables. So, how on earth are we going to be able to find the distribution of this maximum? Well, it turns out that with the using the reflection principle is actually not that bad. So let TA be hitting time of level A. And WT as in star, but with T replaced by TA. Okay, so let's draw a picture. So here's my original Brownian motion. So that's BT. Here's my level A. So this is TA down here the first time that I hit, and notice this is a random. It's a random time that I've got here. It's not a fixed time. I couldn't work out where this was without drawing the random path. Well, then what is W? Well, W agrees with B up until this point, and then it sort of reflects. Okay, so we've got the reflected process there. Okay, so I'll just show how we can. Maybe I'll do it on this board so that we can keep that picture here. Okay, so let's just look at the probability that MT is greater than or equal to A. So this is what we want to work out. So I guess I'm kind of doing things backwards. I want to understand this. So I want to understand this kind of expression for a particular value of A. And so for this particular value of A, I do my reflection. Well, what can we write this as? Well, we can write this as the sum of MT being bigger than A and BT being bigger than A plus MT being bigger than A and BT being less than A. Okay, now in this first case, if I know that at time t I'm bigger than level A, then I know my maximum has to be bigger than level A, right? Because my maximum is the maximum across the whole interval. And so if my final point is bigger than A, then definitely my maximum is. Okay, so this one here is just equal to probability that BT is bigger than or equal to A. And we know what this distribution is. This is just a normal 0t random variable. So that bit's fine. This one is the tricky bit. Okay, so let's have a look at this, the second term over here and see what we can do. We'll observe that this event, mt being bigger than a, is exactly the same event that ta is less than or equal to t. Okay, so if my maximum is bigger than a, I must have hit level a before time t. So these two events are the same. And so we can write the probability that mt is greater than or equal to a and bt less than or equal to a. Well, that's just equal to the probability that ta is less than or equal to t. I've just replaced that by that because these two events are identical. And then I've sort of thinking about my reflection principle, I'm going to write bt less than or equal to a in the form bt minus 2 bta is less than or equal to minus a. Okay, so all I've done here is at the hitting time of level a, the Brownian motion takes the value a. You sort of see that very clearly. At the first point we hit, we take that value. So I've subtracted 2a from the left-hand side, and I've subtracted 2a from the right-hand side. So that's all I've done here. I've used that bta is equal to a. Okay, but what is this? Well, this was exactly the way I defined wt, because I'm in the situation where I'm bigger than ta. Remember, wt depended on whether this happened or not. In the situation where t was bigger than this was exactly this is minus wt. And so this is equal to the probability that ta is less than or equal to t and wt is greater than or equal to a. Okay, but if I know that my process is bigger than a, then I know that this has to have hit level t already, right? Because there's two cases. Either this hasn't happened, in which case my w agrees with my b, but if my w agrees with my b, then my b is bigger than a, which meant that must have happened, all right? So that can't be the case. So that means that this must have happened, and so I can just remove that completely. And so this is equal to the probability that wt is greater than or equal to a. Okay, and I know that wt has exactly the same distribution as bt, and so putting this in, I now know that probability that mt is greater than or equal to a is equal to probability of bt being greater than or equal to a plus probability of wt greater than a. But this is exactly the same as bt, because these are both Brownian motions by the reflection principle, and so this is twice probability that bt is greater than or equal to a. Okay, and I know what the distribution of this is, and so that means I know what the distribution of that is. Okay, and so using the reflection principle, I took quite a difficult problem, trying to understand a supremum over uncountably many random variables, and I showed actually I can write down the answer explicitly. It's just twice the probability of Brownian motion exceeding a certain level. Okay, so I should definitely stop there. But as I said, and again in the exercise sheet, you'll have some more chance to play with this reflection principle and do some questions involving that. Okay, just any final questions? Okay, so next week we'll do one more section on Brownian motion, and then we'll start looking at martingales and possibly start to move on towards stochastic calculus. All right.